9.7 is our last section in Chapter 9. Chapter 9 goes out with a bang. Solve quadratic systems. We haven't done systems of equations since Chapter 3. In Chapter 3, we did linear systems, systems of linear equations. And one of the things we learned was that if you're talking about two lines crossing, two lines only ever cross at one point. But as soon as you include quadratics into your systems, because some of the graphs can curve, you drastically increase the number of possible solutions. When you have a quadratic and a linear equation, and you're putting them into a system, the number of intersections doubles. Possible, I should say. The possible number of intersections doubles. It is possible for a quadratic and a line to never cross. And it's possible for them to cross once if it's tangent, and it's possible for them to cross twice. When you have two conic sections, it is technically possible to have a total of 4 points of intersection. Here's an example of a hyperbola intersecting an ellipse with, alright, there. 4 points of intersection. I did not draw that very symmetric, for which I apologize. 4 points of intersection. You can have up to 4 if the two equations are quadratic. You could have any number between 0 and 4 if they're both quadratic. If one of them's linear and one's quadratic, 0, 1, or 2. The only way to know for sure is to kind of get in there and dig it out. So that was a number of solutions. Watch out, because unlike Chapter 3, these can have several solutions. Don't forget, when you take the square root on both sides of an equation, you need to put a plus or minus, and that's going to be the part that generates extra solutions for a lot of these problems, because there'll be a positive answer and a negative answer. So the first thing we're going to look at then is graphing. Now for this year, if you have one that you're expected to solve a system by graphing, they're going to be possible to graph on your calculator. Technically, any equation you could graph would give you a reasonable approximation for its intersections with, if you graph both equations, wherever the graphs cross, those are your solutions. So especially in the case where you know that whoever's giving you the problems expects you to have nice answers, you can approximate your solutions fairly easily if you can sketch the graphs really quick. This particular example seems to me like it's been specifically designed to make graphing it by hand annoying because of the numbers involved. So we're going to graph this system using our calculators. In order to put them into our calculators, the only place we have for graphs on our TI-84 graphing calculators are solved for y equals. So we have to make sure we solve these for y before we proceed. So we're going to do this by adding 3x and then dividing by 5. So 3/5 x plus 49/5. Annoying, like I said. 3/5 x plus 49/5. That's my first graph. The second graph, I just have to take the square root. And don't forget, when you do that, it's plus or minus. Oh, I have to subtract 10 first, I guess. 34 minus 10x. So when you have a plus or minus and you need to graph, you actually have to graph it as 2 rows. You have to graph the positive square root of 34 minus 10x. And you have to graph the negative square root of 34 minus 10x in order to get the full shape. Alright, there's my line. There's half of that parabola, and there's the other half. On your calculator, it's frequent that they will not appear to go up. Your calculator just does one point at a time, and it tries this point, it gets that one. It tries the next point, it's down. It's imaginary. It just doesn't bother finishing the line. But you can, join it up in your head. This should be continuous right here, if we had graphed it as the original one stated. Your calculator is just not very good with the verticality there. Based on the fact this is a parabola, this one's going to have 2 intersections. So on the graphing section, I don't expect your book expect you to find the other intersection, but if this keeps curving and this keeps going down, there's going to be another intersection over there. So the graphs cross right here. That's the top one, right, which I labeled as y2, the positive square root of 34 minus 10x. So in order to find it, I'm going to go into my calc menu, which is here above the trace button, and choose intersect. Now for intersection, instead of left and right for your bounds, it's going to ask you for curves. So I look to make sure this is my line, which is one of the two that's crossing. Now to go up and down, I have to choose which of these functions I think it's actually going to cross. And I think it's going to cross the positive one, y2, which is the positive square root, not y3, which is the negative square root, y2, the positive square root. And then it says guess. I'll get close to the intersection there with the arrow key, push enter. And negative 3, 8. Because graphing to solve equations is dicey at best, it's approximations usually, I'm going to check my solution just to be sure. So if y is 8, that's 64, plus negative 30 is 34. That's good. And this would give me negative 9 plus, positive 9 plus 40 is 49. So that definitely works. It's really going to bother me that that other point is out there. Yeah, we're going to have to find it. Should I find it by hand? That's crazy talk. No, we'll find it by the intersection tool, but I believe the intersection tool will give you an error if the intersection is not close enough to your window. Let's find out. So I'm going to see where this line crosses my third graph. I'm going to make my guess right here. The calculator should be able to find it, but it's going to be way far off the graph. So yeah, it says no sign change because of how I've set my domain by having my window. So I'm going to have to zoom out a bunch. So here's my line. There's the top half of my parabola. There's the bottom half. Still not crossing on screen. So I'm going to zoom out again. There's my line. Top half. Bottom half. And there's my intersection. So now I can do it. Intersect. Again, it's y1, my line. And I need y3. Because that's the bottom half of this parabola. And I'll get my cursor close. And there it is. Negative 57 and 4/9 and negative 24 2/3. Which wasn't in the answer key for your book. They obviously didn't expect you to notice there was another one down there when you did this on your calculator. Because they think so little of you. Me, on the other hand, I believe you can do it. 57 and 4/9 and negative 24 and 2/3. Not a whole number either. Yeah. Okay, that's graphing, which, like I said, sometimes very nice. And honestly, if you're looking for solutions like negative 3, 8, graphing these by hand would have gotten you probably, if you graph them nicely, get you close enough to pick the nearest whole number solution anyway. Calculator better for decimal ones. So that's graphing. Solve them for y, put them in, find where they cross. Substitution, which was never my favorite, but I like it better than graphing. Sorry about the yelling upstairs. My daughter should have been asleep quite a while ago. Y equals x squared plus 6x plus 7. Okay, so this is my equation then. My equations. One is a line, one is a parabola. I'm looking for 0, 1, or 2 solutions. In this case, we're going to use substitution. Although I am going to talk briefly about elimination. In case you don't remember from Chapter 3, substitution, you pick a variable and solve for it. In this case, we could solve the top equation for y by subtracting 2x. We can solve the top equation for x by subtracting y and dividing by 2. Those are both possible, although neither one of them is as nice as solving the bottom equation for y because it's already done. So looking around a bit to pick the variable that's easiest is what I recommend in this case. Now, solving the top one for y wouldn't be much worse. Solving this one for x and substituting it in, and then you have to square and multiply it. That's a terrible idea. It's doable, but terrible. So I'm going to take this, which says y is the same as x squared plus 6x plus 7. So in my other equation, I'm going to replace the y with x squared plus 6x plus 7, because my second equation promises me they're the same. And now I have only x's. It is quadratic, unfortunately. 8x plus 7 equals negative 5 is x squared plus 8x. Add 5 and I get 12. So I'm looking for two numbers that multiply to 12 that add to 8. Those would be 6 and 2. So x is negative 6 or x is negative 2. Since I know I only have two solutions because one of these is a line, I don't really need to worry about those. If they were both quadratic, then when I stuck these back in to find the y's to go with them, I'd end up with two solutions for each. Well, sometimes anyway, not always. In this case, this one's linear. It's going to be much easier to use. Although I guess this one's already solved for y. If you want to use that one, go ahead. I'm going to use the linear one. So 2 times negative 6 is negative 12. Negative 5, so add 12, that's 7. And negative 4 plus y is negative 5. Is y equals negative 1. So negative 6 goes with 7. And negative 2 goes with negative 1. And now I have both solutions to this system of equations. I said earlier I was going to make a comment about elimination, which is the one where you add them together in order to eliminate a variable. I'll show you the one your book gives you for elimination, but I want to mention if you're not told which one to use, taking a look to think about it is probably a good idea. In order to eliminate effectively, you need to line up your variables. So the first thing I see here is that since this has the x on the left, I'm going to have to move that over. So the first equation, I can change it to y equals negative 2x. I'll start over. Y equals negative 2x minus 5. The second one is y equals x squared plus 6x plus 7. Now at this point, I can eliminate y's because they line up nicely and have the same coefficient already. I could not eliminate the x's. If these y's didn't line up as nicely, if one was squared and one not, there's no way for me to eliminate x in this case because there's no x squared term up here. So I cannot get all the x's in one addition problem. I can't actually remove the x squared at all. So I cannot eliminate x even if I wanted to. I can eliminate the y's though if I multiply this by negative 1. And I'll get 0 equals x squared plus 8x plus 12, which shouldn't surprise you because that's what we got for substitution. So lining them up to eliminate is something you can do if they're not already lined up for you. But again, you're going to want to look at it. Just remember, if you're going to eliminate, you must eliminate all of the variables and their squares if that's the way you're going. The extra example I have that your book gave me for elimination looks like this. X squared plus y squared equals 9. Now in this case, not everything lines up yet, although I guess I already changed the spacing. They had this space, not so it lined up. But here's my equal sign. I've got numbers over here, I've got a number here. I really want to move that 3 to the other side. Or this 9 over here, I guess. The x squareds line up. This y and this y squared are not like terms. So it is not possible for me to cancel the y's by elimination. I need to focus on the x's because I can cancel the x squareds. So I'm going to change the signs here. I'll do it in 2 steps. So first I'm going to subtract the 3 to the other side, which gives me x squared minus y equals negative 3. Then I'm going to change the signs, so it's negative x squared plus y equals positive 3. Then I'll add it to the other one, which was x squared plus y squared equals 9. Negative x squared plus x squared cancels. This is y squared plus y. I should have gone the other way. And 3 plus 9 is 12, so I need y squared plus y minus 12 equals 0. Again, this is quadratic, but what I'm looking for here is two numbers that multiply to negative 12 that add to positive 1, which are negative 3 and positive 4. So y equals 3 or y equals -4 are my y solutions. Both of these are quadratics, which means each one of these values could have two x's that go with it. I'm going to go with the top equation because then I don't have to square the y's. So x squared minus 3 plus 3 equals 0. Oh, x squared equals 0, which is plus or minus 0, or just 0. If y is -4, this becomes x squared plus 4 plus 3 equals 0, which is x squared equals -7, which is not possible over the real numbers. So it turns out, despite the fact that I got two y's, there's only one solution here, 0, 3. The rest are imaginary. So there's elimination, we did substitution, and we did graphing, which is really all that you need. So let me know if you have any questions, and, well, have a good Chapter 9 test, I guess.